For question 9 of the practice final, we have the setup here where we have essentially a coaxial cable, it's a bunch of concentric rings, and these rings have either some sort of applied uniform current within them, or air or ferromagnetic material. So I'll set up the problem, and then we'll do some analysis. So we have that right away. We say that our z-hat direction is coming out of the page of the paper. So in this case, I've drawn the circle with a dot on it, and then we can see that we have two uniform currents. One of them is in region 1, which I've labeled the regions 1, 2, 3, 4, and 5. 5 is outside of the coaxial cable, and that current within region 1 is I naught times z-hat direction. So it's flowing, as you can see here with the circle with the dot, in the same direction as z-hat. The current in region 4 is of the same magnitude, I naught, but in the opposite direction, so it's flowing into the page of your paper, like this with the cross. We have essentially this material that's conducting in here in region 1. Region 2 is air of this coaxial cable. Region 3 is the ferromagnetic material. Region 4 again is this conducting material with the current coming into the page. And then region 5 outside the coaxial cable is air. The question asks that we want to find the auxiliary magnetic field H in regions 1, 2, 3, 4, and 5. So pretty much the entire distribution of H across our coaxial cable. We'll start by recalling that H is simply the auxiliary magnetic field that's resulting from free current flowing. It's kind of similar to the electric displacement that we use for free charge. Similar kind of analogy, and we, like with Gauss's law for the electric displacement using the free charge, we have a Ampere's law for the auxiliary magnetic field H given the free current. And this Ampere's law equivalent says that we have the closed line integral of H, the auxiliary field, dotted with the area, or sorry, the infinitesimal line element dl, is equal to the free current enclosed by some Amperian loop, which in this case we're going to say we have an Amperian loop that is always centered at the center of our coaxial cable, and we move outwards in radius s. So when we're looking at region 1, our Amperian loop is going to be within region 1. We're moving outwards. Our Amperian loop is in region 2 when we're looking at the auxiliary field in this region. I'm not going to draw them in the diagram because it's going to get very busy real quick, but you can always center your Amperian loop at the center of this coaxial cable, and due to symmetry we move outwards radially at some radius s of our Amperian loop. We can draw that loop in, and we consider the free enclosed current within that Amperian loop, and that's what this equation gives us here. So I'll see if I can squeeze all of the parts into this small space I have over here. So for part A, I'm looking for the auxiliary field in the first region 1. So again, we simply start with Ampere's law, which is just H dotted with dl, given by the free enclosed charge by our Amperian loop. So our Amperian loop, this integral on this side, essentially is always going to have the same form because we're always going to choose an Amperian loop, again, of radius s, which has line element 2 pi s. If we go around the entire circumference of that Amperian loop, the auxiliary field H will always be parallel to that line element, dl. And in that case, we will always be able to pull this H outside of the integral. We have a closed integral around the entire circumference of the loop, which just gives us 2 pi s. So this side of the Ampere's law will always be the same. And then we just have to look at the enclosed current, the IF. In this case, what we can always do is we can look at essentially the total current that is enclosed within this region, and then the Amperian loop will of course enclose some sort of fraction of that total current. So the total area of this inner region is going to be pi times a squared, pi times the radius squared, and we're going to consider some portion of it, some portion covered by that Amperian loop, which has a radius s, so pi s squared. And the magnitude of the current in that region that's flowing, the free current, is I, given from here that we say in region 1 there's a current I flowing in the z-hat direction. So what this means is that the amount of free enclosed current from our Amperian loop of radius s is simply the ratio of the area that loop encloses of that region over the entire area of that region. So just pi s squared over pi a squared. Of course, we're going to get some cancellations, and we can solve through. I will save the algebra for trying to save some space, but we'll say that H is simply S times I over 2 pi A squared. We can see that pi's will cancel. We'll divide by 2 pi S. One of the s's will cancel, and we'll end up, this is the field. And of course, we are flowing in the phi hat direction as we look around the Ampérian loop, and we'll have our current pointing in the z hat direction, and we'll flow around using the right-hand rule, which gives us the phi hat direction. So this is our auxiliary field in region 1 is S times I over 2 pi A squared. For B, we are now looking at the auxiliary field in region 2, so in this space of air just outside of the inner coaxial cable. And of course, again, we look at our Ampere's law, which is just H dotted with dl is equal to the I free enclosed. And right away we have H times 2 pi S, because again, this left-hand side is the same. And this is just equal to I, because now our Ampérian loop of radius S will completely enclose the current that's within region 1, because the Ampérian loop is completely in region 2. So all of the free current that's flowing, there is no free current in region 2, only that's in region 1, it's just I. So our auxiliary field H is simply I over 2 pi S. And I believe this is in the S hat direction. Excuse me. And this is as expected, because this is the same magnetic field that we would expect if we just had a line of current with your current pointing in the I hat direction and your magnetic field flowing around. So I guess the magnetic field in this case will be flowing around, so it's actually going to be in phi hat, if I think this is correct. So again, this just comes from the expected magnetic field that you would see if you just had a line of current flowing. This auxiliary field is the same. The difference between the two is that for the magnetic field, we have that factor of mu naught. In this case, we do not, because of how H and B are related. That factor of mu naught is what's the difference. We can now look at region 3, which is this region of the ferromagnetic material. And again, we have the curl of H dotted with dl is equal to I free enclosed. And this is the exact same as B, because again, there is no free current flowing in this ferromagnetic material. So right away, we can just say that H is I over 2 pi S, and it's phi hat. For part D, it's asking for, excuse me, the magnetic field, the auxiliary field in the region 4, which is the other region that has some sort of free current flowing within it. So this one, we have to be careful. It's not going to be the same as B and C. H dot dl is the free enclosed. And again, we have H times 2 pi S, which is the same. And on this side, now we are going to completely include the current that's of region 1, such the free current from region 1, which is just I. And now the current in region 4 is flowing in the opposite direction. So we're going to subtract that from the total free current that we see if we call the positive z-hat direction the positive direction. And the amount, or the ratio, of this current I that is in region 4 is again given similarly as we have here, the ratio of the areas. In this case, however, we have to consider what is the radius that we're looking at of the region of the material. So on the top, we're going to have our S squared minus C squared with a pi factor in there. I'll include the pi on the top and the bottom. The S squared comes from the fact that our Ampérian loop is at a distance S away from the center, and the C term comes from the fact that our region 4 doesn't actually start until we're at a radius C away. So our material only starts for region 4 of the flowing current when we're at that radius C. So we can't just say that we're at a distance S squared away, because not all of the material within that Ampérian loop is going to be the material that we're considering. We're only looking in the region S squared minus C squared, which is the Ampérian loop to the inner radius C of our region 4. Similarly, on the bottom, we're going to do the same thing, but now we're from outer radius to inner radius, which gives us D squared minus C squared is the total, essentially total distance, or the amount of area that we're looking for of this concentric circle in region 4. So this is the ratio of the current that we need to subtract from our free current of the enclosed region 1. given that we have the Amperian loop totally enclosing all of the charge all of the free current in region 1. There is none in region 2. There's also none in region 3. And then this is the ratio of the amount that we see in region 4. By doing this out, we can factor out an I, and we get 1 minus s squared minus c squared over d squared minus c squared. But I'm just going to factor that out quickly to save some space. You can check at home that this is actually what it equals. But I have d squared minus s squared over d squared minus c squared is our right-hand side. Again, the pi's cancel. We have 1 minus this term in the brackets. We can make a like denominator, subtract some things, and this is what we end up with. So finally, if we solve for h, we get that we have I over 2 pi s times d squared minus s squared, or d squared minus c squared, in the phi hat direction is our auxiliary magnetic field within region 4. This is probably the most challenging one to find, just because we have to consider the fact that there's also current enclosed in region 1, and we're considering all of the current that's enclosed by our Amperian loop in region 4, and the Amperian loop has some radius s. Finally, for part E, this is the last one, we look in region 5. This is super easy because we have the curl of h dot dl is equal to the free enclosed current, which is simply I minus I, because any Amperian loop completely encompassing this coaxial cable will include all of the current from region 1 and all the current from region 4. These are equal and opposite in magnitude and direction, which means that we have I minus I, which is 0, and our h in this region is 0, because there is no free enclosed net current. And that is the problem 9, so I'll quickly run through again my logic. So we initially had this diagram where we have 5 different regions, 4 within the cable, and the 5th region is everywhere outside of that cable. Region 1 has a current flowing in the positive z-hat direction. Region 4 has the current that's equal and opposite flowing in the negative z-hat direction. 2 is air, 5 is air, 3 is some ferromagnetic material, and we want to find what is the auxiliary field H in each of these regions. We can do that by recalling that we have an Ampere's law equivalent for the auxiliary magnetic field, which is just h dot dl. The closed integral of that is equal to the free enclosed current within that Amperian loop. We will always have the same term on this left-hand side of this equation, because we have that the auxiliary field will flow around in the same direction as our infinitesimal line element dl. So this dot product will always be parallel, which just means we have the magnitude of each multiplied together. The dl gives us the circumference of the Amperian loop that we choose, always centered at the point in the middle of the circle, moving out in some radius s. This allows us to always have h 2 pi s on the left-hand side, as we see for parts A through E. And the right-hand side, the free enclosed current, is what's going to change depending on where we are in our setup. So for part A, we're looking at the amount of free enclosed charge within region 1, which is just given by the ratio of the total area that has that current flowing within it, with the numerator being the amount of enclosed current given by our Amperian loop. In B and C, both of them, we see that the Amperian loop completely encapsulates all of the free current that's flowing within this inner region. The ferromagnetic material, you might think there's some current flowing within there, but usually this is bound current, because there will be some sort of induced magnetization within that region, and it's not a free current that's flowing. It's similar to the electric displacement with Gauss's law, and when we see with parallel plate capacitors and things like that, where you have the amount of free charge is the charge that is able to flow, it's able to move around, it's what we essentially kind of embed within the system. Here we only have free current in region 1 and region 4. D is probably the most challenging, because we have to have the inner current component from region 1, and we subtract off the current that's flowing in the opposite direction in region 4. We could do some algebra and figure out that this is the auxiliary field. And finally, outside of our coaxial cable, we have essentially the current flowing in region 1 is equal and opposite to the current flowing in region 4, which means that they cancel out and there is no net free enclosed current, which gives us that the auxiliary field is simply 0. So these are how you find kind of conceptually and mathematically the auxiliary magnetic field in each of the 5 regions.